All right. Good morning. How is everybody doing? Who's ordering pizza today? We're going to discuss first the famous homework number 4. That was a lot of fun. I have to say I'm actually pretty happy with what you guys have done here. The spread is even broader now, but I think it managed to push you to think, so that was the whole point. All right, so Shayala is not here. You on?
Yep.
Alex? Kinlan? Nope. Jose? Daniel? E. Sun? Fu? Are you guys related? Fu Sun, E Sun. Chao E? Is that how you say it? Yeah. Roughly. Rui? Caitlin? And Kelly. Okay. So, well, I calculated the average and stuff, but I don't remember what it is. I know the spread was large, like 16, 17. So we do have maxima of 100, but we do have minima of 46, I think. Hold on, you're auditing? Okay. Okay, so problem 1. As usual, we're not going to solve it in great detail, but just get the starting point. I think actually problem 1, at least part A, pretty much everybody did. Okay, so the problem was to write this scattering potential F of R. So N1 is the bigger one, so it's going to be N1 squared minus 1. Okay, N1 squared minus 1, blah, 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 K naught squared over 4 pi. Yeah, who cares? So that will be F1. Now F2 is actually just the difference. And shall I have your homework 1 and 4? Okay, so this is just basically, if I assume the outer sphere is in 1, then writing the scattering potential for the inner one is just N2 squared minus N1 squared. That was the only basically trick here. So when you write it together, F will be this plus that, right? And then taking the Fourier transform of this is as usual. Okay, so each of these has a rectangular function, right? This of R1, this of R2. And then the Fourier transform of this will be whatever, so let's say f of q will be with n1 squared minus 1. All this k squared stuff. And then we know what this function, the Fourier transform of that is, the sine of x minus x cosine of x, blah, 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 blah. Plus the same thing here. Blah, 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 blah. So now, in the next point, we're asked to discuss what happens when n1 is bigger or smaller than n2. Everybody on board with this so far? So as usual with these scattering problems, if you know how to write the scattering potential, you're kind of done. So the main trick or challenge was to write this as the difference between. So sphere 1 becomes the background for sphere 2, kind of. Okay, but problem 2 was a little bit less well defined, and I ask you to oh, that's C. Okay, so B is asking to do the same thing. If we shift sphere 2 by delta. So the only careful thing here was to write properly in a vector form that displacement. And I've seen some of you didn't do it properly. So if you just write r scalar, so the new r prime becomes r minus delta scalar like that, that's terrible, right? That's going to give you the wrong result. Because always keep in mind, whenever you write r, which is the coordinate, you write it as a scalar. That's a radius. Okay, so when you subtract something from the radius, you basically make the radius smaller, but you still get kind of describing a sphere that now it's smaller. So it's nothing to do with our displacement. It looks close. Okay, so the proper way to write the shift is that my r prime is now r vector minus delta, and I'm looking along which direction. I think I told you it's along z. So that's it. Once you are able to write this, then pretty much you can apply the shift theorem, but now notice the shift theorem. So I'll give you the homework in a minute, okay? The shift theorem applies on a one-dimensional space along z, along the direction of the shift, right? So now it becomes kind of transparent what that shift does. So basically, we just we input this new r prime into your scattering potential of R2, right? So R1 is the same, except F2 now is N2 squared minus N1 squared. But now this is R, which is R minus delta times Z, magnitude squared. Okay, so this is rectangle over 2R2. Right? So the difference with respect to the unshifted case is that now your sphere is basically shifted at the new coordinate. That's all that says, right? So it's going to be times, x squared plus y squared plus z minus delta, everything squared over 2R2. Okay? But already, if you leave it in this form, when I take the Fourier transform back, I'm going to get, let's say, F2 of Q equals N2 squared minus N1 squared. This stays the same. I carry it just for the next question. And this becomes whatever I had before, that sine of QR, blah, 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 sine of QR minus QR cosine of QR. Is that over QR cubed? Yes, and an R cubed here. This should be R2, right? The sphere. So R2 cubed here. And now what's going to happen along this dimension? I'm going to get my shift e to the IQ delta. Except Q is QZ. Yeah.
If you have a positive shift on Z, should the exponential be negative, or does it matter?
Say it again?
If you shift along positive Z,
yeah.
Do you need a negative sign up top, or no?
So first of all, this is shifting a positive Z, so my function becomes Z minus delta.
Yeah.
Right? So therefore the phase shift becomes plus I delta in our convention of Fourier transforms. If you change the sign in the Fourier transform from minus I to plus J, like some of you do, some of us do it differently, then it will flip the sign. But it has to be everywhere.
Right.
Okay. Yeah? Are we okay? So basically, I think the ones who missed this problem, those of you who missed this problem, maybe you can track it down to writing this shift wrong. And it has to be a vector. The shift has to have a direction. It's along Z. Once you have that, then basically, you see how easy the calculation becomes by using the shift theorem. So now the interesting part is C, where I asked you kind of an open-ended questions there just to, have a stream of consciousness and explain what you feel about this. What if we switch between N1 and N2, we switch the sign, meaning the nucleus is higher than the cytoplasm versus the other way around. And the interesting thing there was, and some of you noticed that, is that if I go from a plus to a minus, let's say magnitude of N2 minus N1, this is what we're talking about. It's the same as writing e to the I pi or e to the I times 0 times the same thing. Meaning, if I switch from a positive, if I switch from N2 bigger than N1 to the other one, I basically get the phase shift of pi between the two terms. So essentially, the problem is really, the scatter field is really an interference between the contribution of one sphere and the contribution of the other sphere. And if I change the sign between their refractive indices, I basically interfere these two, but now with the pi phase shift between them, which is kind of interesting. Maybe some of you know that when I have simple reflection at an interface, so imagine I have glass here, 1.5, and I come from air, and I reflect off, I get the pi phase shift. It's kind of the same physics. If this is smaller than if I send it backwards, like that, there is no phase shift. Yeah? Okay, so that's something. So it's really an interference problem, and that sign change gives you essentially a pi phase shift. But now the even more interesting thing is, if I shift one of the bit in Z, I get this phase shift, which acts exactly like this phase shift. And I think somebody pointed out that I can make my shift delta such that it compensates my pi perfectly. Meaning, for a particular QZ, I can make my delta such that the final signal looks as if the spheres have the opposite refractive index. Do you see what I'm trying to say? So if you switch the refractive index, let's say make N2 smaller, you get the pi phase shift. And I can compensate for that if I just shift the sphere along Z by a little bit. Which is terrible news for an experimentalist. If you are in the business of trying to characterize the refractive index for cells, this is something that I don't think I've ever seen like published or really described properly. that this very simple thing, so the nucleus is just displayed a little bit and it looks as if it has lower refractive index than the cytoplasm, right? But the physics is kind of clear why that happens, because this is really an interference between two complex fields, so they add actually in phase and amplitude. So we have to be really careful. The displacements play a role. If you just look at individual intensities, nobody cares. You wouldn't be able to tell any of this.
I have a question.
Yeah.
The F2, it has N2 squared minus N1 squared.
Yeah.
But it's actually described the second sphere, so I think it's N2 squared minus 1, right?
Well, I put already, because the sphere is already covering my second sphere. The sphere 1 is covering the material of sphere 2, right? So in order to add, right? So I already, where the sphere 2 is, I already have sphere 1. Okay, so it's kind of sphere 1 is already the background for sphere 2. Everybody agrees with this? Is this wrong? Yeah? I've seen in some of your homework, some people say more. So I think most of you kind of got the idea that there is something interesting happens when this N2 changes sign. But the conclusion was a little wrong. Some of you said I get more scattering or less scattering. So now, since we are professional optics people, we should really describe what do we mean more scattering. What's more scattering? It's either more power or something, more phase, more something. More scattering is kind of meaningless. So clearly, you cannot say whether you get more power or not just by looking. You cannot just say I get more power if the refractive index contrast is positive or negative. You have to look at particular cues. You know what I mean? So if we look here, this is the summation of the two fields, right? This is an interference. Now, each is a complex function, each of these fields, right? So you may be tempted to say, oh, this is bigger, therefore I get more power. No, not necessarily, because you don't know the phases of this. Actually, they could, for a particular Q, so I have Q in here, right? Q in here. For a particular Q, there may be an anti-phase that you get the 0. And actually, it will be an oscillating function, and you don't know a priori how it's going to look. You may get 0, actually, 0 power. Okay? So just because this changes from positive to negative doesn't mean more power. You have to be looking at the intensity, meaning taking. So if I want to write the intensity of this, I have to do I of Q equals magnitude square of F of Q. Right? And you have to, just one second. So that will give you the intensity from one sphere, the intensity from the second sphere, plus 2 times square root the intensity of 1, 2, and then cosine of the phi 1 minus phi 2. So yes, when I switch the refractive index contrast, I introduce here a pi. Right? But that may, according to, depending on what Q I have, depending on the value of Q, meaning depending at which angle I'm looking, these may make it better or worse. It may give you more power or less power. It's not clear. It will be different, that's all you can say. But you cannot say I get more power necessarily. It's not true. Definitely not true for all the Qs. Remember, this is an oscillating thing. Yeah.
So I thought when you said power, you meant power across the whole field, and that would make sense by conservation of energy. But you mean Q for a specific Q, what intensity you get, right?
Yeah. What? Power across?
There's no attenuation term in here, right? So theoretically, the incident field you put in should be the same total power you get out.
Oh, yeah, sure. Yeah, we're talking about power along a certain direction, right? This is what we call intensity, right? Is watts per steradian. What we usually call intensity is actually irradiance. So you guys know this?
What's per meter squared?
Watts per meter square. This is what most people call intensity, but it's wrong. Okay, so but since you are professionals, okay, so watts per meter square is actually irradiance. All right. So you got the idea, right? That it's actually quite interesting, and from an experimental point of view, when you try to characterize cells like this, you always come up with a model. Oh, I told you about everybody calling them spheres and using the M.I.T theory. And not only that, if you use M.I.T theory, you actually cancel automatically this connection between these interference terms. This is what bothers me personally the most, that you say the tissue is made of spheres that are independently scattering, meaning the light scattered from one particle does not interfere with scattering from another particle. And that's totally wrong in the tissue, because they are really close. And that, you see, it can make a huge, huge difference. Anyway, I thought this was an interesting thing, that by just shifting one sphere with respect to the other, you can get something along, at least along a certain direction, that looks as if you switch the refractive index around. Which, as I said, complicates things if we're trying to understand how the refractive index looks like. Okay, so really this was an open-ended question where I wanted you to just, make up stuff and think about it a little bit. But I think for the most part, problem one was maybe your best. Any other questions about problem one? So you can imagine now, recently we started working with embryos. So you can generalize this. You can make a sphere that's filled with many other spheres, actually, which becomes an even more interesting thing. So in an embryo, you start with a big egg like this, about something 200-300 microns. So you start with one cell, and then they start to divide. So you have 2 cells, and then each divides 4 cells, 8 cells, and so on, and so on, and so on. And you end up maybe with dozens and dozens of cells, but constrained to the same outer shell. So I think you should be able to treat any arbitrary of that kind of problem now. So any arbitrary number of spheres, arbitrary numbers of their positions, right? Should be no problem, right?
You're working with embryos?
Yeah? Bovine, not. Yeah, it's quite interesting, actually.
So if you want to characterize the refraction index of a cell,
Yep.
you either want to make the nucleus still, or you detect the move of the nucleus in the cell.
Oh, now you're talking about dynamics, okay. So it's a question for me, what I want to do in our lab, or?
Yeah, so how do you characterize the refraction index of a cell correctly?
Okay, well, I think that our best chance is to actually do a tomogram, okay? So, meaning solve that inverse problem. From all the Q's around the cell, actually take the Fourier transform inverse and get back to the chi, right? So in our lab, what we do, we use this wide light interferometry, which has a very short coherence length. We're going to talk about optical coherence tomography and see what that coherence does to your sectioning. But so we basically slice this through focus. So imagine you take a phase and amplitude image at each position in Z, and then using the Born approximation, we kind of reconstructed 3D structure. So at the end of the day, what you get is exactly, or at least an approximation of this function, which is chi of R, the refractive index at all 3 points. So the reason it sounds easier than actually it is that you always miss Q's. You miss ranges of frequencies, no matter how you do it. So what that actually gives you in real life is that your cells look distorted. They may look elongated along Z. you have artifacts due to the reconstruction. So that's kind of one challenge. There are other ways to do it. Other people use it simply more directly related to this problem is to illuminate and measure at different angles. So it's kind of like the X-ray tomography, like X-ray CT type of idea. But it's all really built into the Born approximation. Some people use the Ritov approximation, which is a sister technique that we didn't talk about. But yeah, so any shifts, if you collect all this entire space of Qs, then redundancy goes away, right? What I mentioned about this confusion that when you shift along delta, it may looks like the refractive index switch. That means you rely on a single Q. So that clearly gets you into trouble. So what we do in people like us, what we do in real life, we try to cover as many of those Qs as possible such that your reconstruction becomes unique. Do you guys know, anybody knows what Ritov approximation is? It's related to Born, but. No? Oh, well, since we brought it up, just. Ritov versus Born. So in the Born approximation, we simply expanded the field as U0. So this is the incident field plus U1 plus blah, 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 blah. Right? So we only keep the first order scattering. We neglect any multiple scattering. In the Ritov, you get actually this expansion, but in the phase itself. So you get phase 0 plus phase 1 plus blah, blah, blah. That's the only difference. So now, if you look in detail, actually, Professor Wang Chu has a book on light scattering, and he's really explaining this very, very clearly. I think the book is called something scattering. I don't know. Electromagnetic. Wait, look for Chu's book. You'll find it. Okay, so this, roughly speaking, this works when your objects could be bigger than we like to have for Born, but they cannot be too structured, so they have to be smoother. You see? So that's when you apply Born. When you have something, if you do aiming for a reconstruction that's lower resolution, so smoother objects without too much stuff inside, then probably Ritov is better. We always use Born because really we want to get high resolution imaging from the cell, so close to the wavelength, where this works better, but the constraint is you cannot have too thick of an object or too much of a refractive index change. Okay, that's a parenthesis, just in case you hear about Ritov. It's kind of a sister technique to Born with kind of complementary application range. Okay, should we move to the next problem? Are we okay with this? So do you know if I give you for the exam, I give you an embryo with 50 cells, you know how to do it? I'm not going to do that, but I can give you with 12. I mean, it's really this, kind of. It's the same philosophy as here, right? It's all about describing the shifts. So if you're able to write the shifts, so place your spheres in the proper places, then everything else is just math, yeah?
Okay. We don't have to substitute in for Q and put in K incident minus K scattered and try and expand that out. We just need to solve for Q, right?
I gave you full credit whenever I saw the correct, in terms of Q. I think that's fine. If you put the shift in there, it's okay. Of course, when you want to write it with respect to an angle versus my incident light, which is, I think, in the problem 2, yeah, with respect to that phi, yeah, you have to express that Q as a difference, but that shouldn't be a problem, right? Okay, moving on. Okay, so cylinder. So basically here what this homework is about is to try to make you, to give you this message that really the approach is kind of the same everywhere. Okay? So this is, once you know how to do one, you should be able to do all of them. The only difference is the math. Okay? So here you have a rotation matrix. But it's not a big deal. I mean, the physics, once you are able to write the chi down, the physics, you pretty much you solved all the problems. So that's kind of the idea. Okay, so here what do we have? Well, we have a particle that is not as straight as I want it to be. It's at a weird angle. Let's say theta with respect to x. I was nice and I said the incident is at least along z. So you have two options. You either, so first of all, you write chi for a straight cylinder, right, as if you are in its own system of reference. And you either rotate the cylinder or you rotate your incident light. And I think many more of you rotated the cylinder, which is perfectly fine. A couple of you rotated the incident light, and it's much faster if you just rotate the incident light. You have to be careful. The formulas would look totally different. So the people that rotate the cylinder and the people that rotate the incident field, they get different formulas. Why? How is that possible? Yes, they are basically expressing their fields in a different system of reference. So the people who chose to rotate the cylinder, they are in my system of reference, this one that I drew here. Okay, so their Q will be expressed with that. Their QX, QY, QZ will be with respect to these components. Once you rotate the K incident, what you assume is that, well, my system of reference is actually this now. And therefore, my scattered light, my QX, QI, QZ will have components actually projected onto that system. So the formulas look different. Of course, going from one to the other, they better give you identical results. But you have to do this rotation. So I didn't care if you rotated the incident and you left it in this system of reference. That's okay. Do we need to write it down line by line, or?
Sure, that'd be helpful.
That would be good. Okay. Thank you, Alex. I'm gonna copy it from here. Oh yeah, so I asked you to plot also in Formula 1, in problem 1. Before we do that, plot. So some of you did a great job with the plotting. Some of you took shortcuts and just plot sinusoidal things. What I was expecting here, since I didn't give you any number, I was expecting you to kind of make up your own numbers. Like, I'm going to look along this direction or something like that. I'm going to make this cylinder this big. And some of the graphs make sense. I have no way of saying, unless I know your numbers, I'm not going to be able to check. But having just a simple sinusoid, that is the wrong answer. I can tell you that. And also, some of you looked at the shift and how it changes the graph. I think you did a good job with that. And it's pretty amazing, actually, that small shifts can actually do a big change in your angular scattering. Oh, so that was the idea with that problem. Okay, so let's write down the rotation matrix. So my new coordinates are x prime, y prime, z prime, are the rotation matrix for angle theta, and it's along y, right? Yeah. Times the old ones. And this rotation matrix is basically cosine 0 minus sine 0, 1, 0, sine, 0, cosine. Is this true? So, I got it wrong. I think because I defined my theta wrong, right?
If it's counterpolarizes correctly, and you just change it to minus theta.
Yeah, okay, so let's do it the way it's in the, okay. Some of you pointed that out, that my theta is measured not the usual way. Okay, so it's actually sine of theta. This is minus cosine. This is cosine. And this is sine. So you know one way to check is that the determinant of this matrix is always 1, right? And basically it's an identity matrix along y, so it's only x and z that changes. That means rotational log. We okay so far? Yeah. Okay. So that means that when you do this calculation, my x prime will be x sine of theta minus z cosine of theta. Y prime stays the same. Z prime equals x cosine. Okay, so just expanding that multiplication. Okay? So basically what this does is now your particle scattering potential, so FP of x, y, z of r equals, so along the x and y I have a disk, right? So this will be pi. I should discipline myself to write the rectangular function, which I like so much. I should put 1, 2, 3, depending on which. Wouldn't that be helpful? Okay. So this is now the disk, right? So this is square root of x sine of theta minus z cosine of theta squared. So this is my new x. This is x prime plus y squared over 2r. And then this whole thing is multiplied with the one-dimensional rectangular function along z, which is x cosine of theta plus z sine of theta over h times n squared minus 1, or whatever, right? That's the, with beta squared, blah, 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 over 4 pi. Cool? So pretty much the physics is done right here. It was done before, actually. This is your scattering potential in the coordinate system for a rotated particle. All I need to do to get my scattering field in this system of reference is to take the Fourier transform of this. Okay, so if I don't care for elegance, I can just plug it into MATLAB and that's it, I'm done. Okay, so now what do we know about the Fourier transform of a rotating thing? Huh? The rotation theory, remember that? I'm so glad you remember that. One of you. So what did we find out? That if we take, let's say in 2D, right? If I get a certain object, 2D object, I take a Fourier transform. So basically I put a lens and I do a Fourier transform, right? If I rotate that object by a certain angle theta, the Fourier transform better rotate with it, right? So which means that I can write my q's. So basically my f of q is nothing more but the Fourier transform of this. Okay, Fourier transform with respect to r. And your new q prime will be also rotated. So it will be qx sine of theta minus qz cosine of theta, qy, qx cosine of theta plus qz sine of theta. So what you can do is to actually write your unrotated particle scattering and then plug in the new Qs. That's another way to do it. So now let's see if I'm trying to do it the simple way or the simpler way. This is a perfectly good way to do it. But if I'm lazy, wouldn't it be better if I do the rotate the K incident and leave the particle the same? How do I do that? Well, okay, so this is second solution. So I'm going to say my Ki prime, which will be Kxi prime, Kyi prime, is Kzi prime, equals, so the same rotation times my old ones. Kxi, Kyi, Kzi. So, yeah, so basically I have the formula for the unrotated particle. So my F particle of R is just pi of R, let's say R perpendicular, so this is xy over 2R times pi in one dimension, this is in two dimensions, of z over h. So this is my particle in its own system of reference. And I know the scattering of this, f of q, the scattered field will be whatever, this is a jink times a sink. Except now my Q is, so they're all QR here, right? Except my Q is the Ks minus Ki prime. That's the only difference. So basically I take my rotated coordinates and I plug it in here and I'm done. So it will be Ks minus, and here what am I going to have? I'm going to have, so I can write Ksx if you want. I can write the coordinates like this. How about that? So I can write it like this. So it would be Ksx, Ksx minus. Now the rotation of Kx will give me also something like this. So Kx sine of theta minus Kz cosine of theta. So that will be this will be my Qx prime. Then my Qy stays the same. So it will be, let's just leave it Qy. And then this will be my Qz prime, where I'm plugging in Ks minus blah, 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 this one. You know what I mean? So let's write it down. So it will be Ksz minus Kx cosine. Oh, this should be plus here, right? So it's minus parentheses. So this is minus Kz sine. So notice, this is the same as the unrotated particle. It's just I'm evaluating it at different Qx, Qi, Qz. And since Qy is the same, I only have to change the Qx and the Qz. And actually, the only difference in the Qx and Qz is through the K incident. The Ks is the same. So this looks much simpler than before, where we had to change coordinates inside here. That's the difference. Okay, so the formulas are totally different. Why? Because they are in different systems of reference. This gives you the scattering with respect to the rotated particle. So it's like, this is my new system of reference. that's why. Yeah? Is this okay, Alex? Great. All right. Let's see. Then, I mean, if you did this, then the next question is, as difficult as it may sound. Imagine if I asked you first this question. Oh, I have a particle that rotates. It may seem crazy to solve that problem, right? But if you slow it down, take it step by step, actually it's very doable. And actually, this could be very useful. I'll tell you in a minute one application, like science paper based on this. So the question is, what happens now if my theta essentially, time dependent, right? So it's a linear, so it's just an angular velocity that is constant, omega. So basically all I need to do is to plug into my theta, make it something like omega t. And if I want to be thorough, I can put the theta naught plus omega t. But who cares? So pretty much that's it. Okay, so you just plug theta as omega t. If you want, some of you were more dedicated than others, and then express the results with respect to theta. So with respect to phi, I'm sorry. So phi describes your components of the ks, right? So you can write it as cosine of phi, sine of phi, and the magnitude is always k naught for both incident and phi, but pretty much that's it. So imagine an experiment where you actually illuminate these cylinders and you look at the fluctuations of your scatter field at a certain angle, and you figure out whether the cylinder is tumbling or not. And there was a science paper actually look at bacteria that pretty much are ellipsoids, but close enough to a cylinder. And they are actually mutating the bacteria, so some of them will tumble, some of them will not. Apparently you can do that. And they worked out actually the diffusion equation, kind of the equivalent of Stokes-Einstein equation. So remember in dynamic light scattering, that equation that gives me the diffusion coefficient with respect to the temperature, with the size of the particle and the viscosity. They were able to derive that for an ellipsoid. So now you have two time constants whether the particle is tumbling. So the particle can shift around like a regular Brownian motion thing, but now it can also tumble. So that's where I came up with this idea for this homework. So there are two different constants. So if this doesn't tumble but moves around, you get your regular kind of dynamic light scattering problem, right? So center of mass translation. But when this starts to tumble, you get on top of that the different dynamics. This has different correlation times, right? As you can imagine. So anyway, there was a science paper on this where they actually were able to distinguish between two populations of bacteria, the tumblers and the non-tumblers. And as a fun fact, it was published close to 2005, which is exactly 100 years after Einstein's first paper on Brownian motion, on spheres. And this was the generalization of that for ellipsoids. So anyway, so that's the history with this problem. You would expect two different decay times, like, I don't know, like this and then like that. One from translation, one from, so this would be our old correlation function. One from tumbling. All right. Problem 3, where most of you started to give up. I think you had enough of this stuff. So by the time we got to C, D, and E, some of you are like, screw it, I'm not going to. So, again, the approach is really the same in all of them. What do we have here? Well, we really have the problem of a crystal, right? This is the problem of a crystal. This is how crystallography works. It's a simple problem in the sense that this has this cubical symmetry. I didn't put atoms in any of the facets. I didn't make it complicated. I didn't tilt the cube. You can imagine you can make a diamond-shaped facet on all of them. So that would be the most general symmetry you can have, right, where the angles are all messed up You can have alpha, beta, gamma in all directions. So that will be a mess. But these are just 8 little particles sitting at the corners of a cube. I come with the plane wave along Z. My cube is nice and straight with respect to X, Y, Z. So first calculate the field, right? So as usual, the difficulty was to write the scattering potential. So I think some of you complicated things here. Well, I would say most of you got it right, but the easiest way to do this is to realize that the coordinates of this, probably the best system of reference is to put it in the center of the cube, and then realize that basically all these particles are essentially beta 2, right, on 3 dimensions. So it's either plus minus beta over 2 on X, plus minus beta b over 2 in Y, plus minus b over 2 in Z, all possible combinations, that's all. So that's why you get 2 to the power 3, you get 8 combinations. So once you are able to write that, so basically Rj is basically equals plus minus b over 2, plus minus b over 2, plus minus b over 2. So essentially, now we have a structure function, right? So the particle scattering potential is easy, just whatever this is. Did I give it a size? Or is it small? Whatever, it's a sphere, so that's easy. The interesting part is in the structure function, right? So the coordinates of the delta function will be delta of r minus rj, where each particle will be one combination of this. I think that's the easiest. Once you wrote that down, so it will be sum of delta of r minus rj over j from 1 to 8, Fourier transform of which will be summation of e to the I q rj. And that will be S of q, this will be my structure function. So at the end of the day, I'm going to get the form function, so the scattering from a sphere as if it's by itself, modulated, multiplied by this S of q. That's it. So it will be a sum of 8 terms, so it will look like e to the I q minus b over 2 plus b over 2 plus b over 2. Complex conjugate of that, some of you noticed that actually they come in pairs, right? There is a symmetry with respect to the center, so if this particle will have the exact conjugate that particle, which means minus the entire vector, right? This is conjugate to that and so on. So you essentially have 4 pairs of cosines, 4 cosines, right? So 4 pairs of exponentials, 4 cosines. But I don't care. If you left it in a summation like this, you got full points. Again, the meaning of this structure function is nothing voodoo about it. It's just accounting for the fact that really we're looking at an interference in far field from all this scattered light. And that exponential keeps track of the phases because we're adding complex fields. Phases are really important. That's all. So it's telling you that this, whether I'm placing a particle at the distance r versus r prime, it makes a difference in my interference. It changes that phase delay. That's all. Okay, so this is the final solution. If you want to look at the intensity, you have to magnitude square all those 8 terms, and look what happens. You will understand what crystallography people are dealing with. It's a mess. And this is a simple case. Right? So you get maximum, minima that are not really our regular sinusoids or our regular jinks. They could get really complicated. So imagine how the DNA was discovered, was based on this. So you crystallize the DNA, meaning you make a lot of the molecules aligned in the same way. Okay, so it's as if I'm adding a periodic lattice to this cube. But now imagine how the scattering from a spiral looks like, double spiral. I Actually, last year I think I gave this problem just for fun. Not that I knew how to do it, but I wanted to learn. There's a formula actually for a Fourier transfer. That's why I gave it as a problem. It's not a simple one, but so imagine you put your particles on top of a spiral, on a double spiral, and illuminate that. It's doable. That's how the Nobel Prize happened for DNA. That's how they figured it out. So you look at the mess of spots, right? It looks like a mess. Maximum, minimum everywhere. It looks like nothing. And then you start to think about it. Which scattering potential matches my diffraction field? And they figure it out. It's all based on this, okay? So whether it's spiral or not, that's really just math. It's a math difference. Physics is the same. Okay, so any more discussion about this? Are we okay with this for problem A? Yeah.
You were saying that you have cosines, obviously, for the two deltas like this, but you have on diagonal as well. Is that what you were saying?
The pairs are symmetric with respect to the diagonal, right?
You're right.
Yeah. So for each particle here, I have another one that on the diagonal. So they are complex conjugate.
And that creates a wave in that normal to that direction, cosine.
Creates a wave. What do you mean creates a what?
Like, if you think of delta as like the two-slit experiment, right? If you have a cosine propagating along normal to that direction, so do you have now a diagonal cosine?
What it means is that if I were to illuminate, let's say I'm picking these two particles, if I'm illuminating exactly on the perpendicular to their diagonal, they will give you a perfect cosine. That's what it means.
Yeah.
Right? Okay. So these two, they give you a perfect cosine if I illuminate this way.
Right.
And so on and so on. That's what it means, that the coordinates, if one has the coordinates b over 2, b over 2, b over 2, which will be this particular one, right, in the first, what do you call a quadrant in 3D? Octadrant? Huh? Octan?
Often, yeah.
Octan, okay. So it's in the first octan here. Then the conjugate one will be exactly negative of the whole thing. So it will be down here, where, that's what I meant by. So in the summation, you can combine e to the I blah 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 with e to the minus I blah blah blah. They give you a cosine. That's all. Other questions? All right. So same as in A. Okay. So now we eliminate along the diagonal, and I didn't say which one. So it's up to you. So what's the difference? So my elimination, let's say, is along this way instead of that way. First thing is the scattering going to change? That should be your first question. Does it matter? It does matter, right? It does matter, because all my, basically because this has no spherical symmetry, right? If it was a sphere, of course it doesn't matter. But in this case, it matters because, for example, this little particle will be hit first, right? So the scatter field from here will have a different phase shift than from here, 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 here. While if I illuminate from here, all these four particles will be hit at the same time. They will be in phase. Okay, so yeah, it matters. It's because it's not spherically symmetric. Okay, so then how do I deal in the easiest way possible with this problem? As usual, I can rotate the cube or I can rotate my incident light. Right? So it's up to you. So probably the easiest is to get your incident. So this is B. You can get your incident prime as Ki, the old one, or k naught, because that's the length of it. And then it's square root of 3 over 3, 1, 1, 1. Right? So if I sum all of these square, I should get 1. So I think that is correct. And before I had 0, 0, 1. Right? Because I eliminated along z, only the z coordinate was 0. Yeah? Alex, okay? Semi? So what it means is that I know potentially this is correct because if I add all the coordinates, I get the same length as before. So the length doesn't change, just rotate. So that's one good thing, but it doesn't mean I'm right. So imagine I have this. So I think this was z, x, y. And basically I'm illuminating with my ki along this direction. And you just do a projection, right? As usual. And the question is what, because I'm over diagonal, I know each of these should be equal. Yeah? So you do the calculation. It's going to come out to having this square root of 3 over 3. And this square root of 3 over 3. And this square root of 3 over 3. Back to high school geometry. Which, by the way, I messed up. Did you notice? In this one, my high school geometry failed me. But nobody, you're very nice, you didn't point it out. So clearly this was wrong. It was a combination of a square and a cube, right? So in a square you get square root of 2 over 2. So this doesn't work with the way I intended it to. It has to be square root of 3 over 3 to work. But what's a square root of 3 among friends, right? Okay, so is that okay? Yeah. So it's really, because this is equally kind of away from all the 3 axes, you get the same coordinate. The only way to get the sum of the squares to be 1 is basically square root of 1 over square root of 3. Okay, so basically once you have this, you just plug in you get the same formula, the same f of q, except now, oops, that's for the cube. You get the exact same scattering amplitude, which will be your form, what do we call it, f0, times s of q at q now being equal to ks minus the new ki, k prime. So it's going to be kx minus square root of 3 over 3 k naught, blah, 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 blah. In the previous case, the first coordinates will be 0 of the incidence. So it will be just ksx, ksy, ksz minus k naught, because the incident had the k naught coordinate along z. Now I have all 3 components. Yeah? So just a rotation, right? You can rotate your cube, no problem. It's going to be messy, right? So, and keep in mind, the formulas are different. So this, for example, it's much simpler, but keep in mind what it means is that I'm expressing my results with respect to this coordinate. No, it's in the XYZ, right? This. Yeah. Previously we rotated the cylinder, that's why it's different. Okay? Any questions about this? It's really like the cylinder problem, except now I rotated the incident field. So it's cool? All right, now we are getting into the I sensed that you started to hate this as we went along. So some of you expressed in words on the homework that please, like Kelly, for example. So, calculate the scatter field if so basically what we're trying to do is, what if these particles are vibrating? And I made it very simple actually. They are vibrating with respect to the center of the cube. And along the diagonal. So I couldn't have made it any simpler than this. Now, first of all, what is the relevance of this?
Real atoms vibrating in the lattice.
Real atoms vibrating in the lattice. Exactly right. Real molecules having atoms around the nucleus and having vibrational modes. You can calculate maybe Raman shifts. You can calculate infrared spectra by a similar calculation. Okay? The difference is when the dipole moment doesn't change, which is this example, so there is no net change of the charge. This is not a dipole active mode, but it will give you Raman shifts. Okay, this frequency will show up in your spectrum if you do your experiment right. Okay? But yep.
So the particles are vibrating along whichever diagonal you choose?
Yes, along their own diagonal in a way, right? So what that means is actually the reason it becomes very simple. It's as if D, you're scaling D. So it's like you're zooming in and out of your cube. So really that's the easiest. So once you understand that, then you scale your B to oscillate and everything is the same. As opposed to, for example, I could have done this. They would be vibrating with respect to each other. Can you imagine that? So now each two will vibrate with respect to one another. To be a little messy, but interesting. Yeah? So really it becomes very simple in the sense that your B, you factor your B and you write it as B equals whatever 1 plus omega t, and that's it. So that will factor all the way out, and it's going to give you some kind of it's going to factor all the way in front, right? Let me see. Okay, let's write it down. You guys still need to explain this sensor thing, okay? At some point. So all I know is that there are 3 variations now of this. Okay. Okay. Yeah, by the way, every year I make sure you don't get a research project that's close to your thing. But maybe another way to do it is to pick one that's exactly your thing. So you have personal stake in it,
Like a mini qualifier?
like a mini prelim, qualifier. Yeah, why not? For you, I think to be more useful, right? To get a low risk rehearsal. But I always thought the point would be to learn new tricks. So that's why I did the opposite. But I don't know. What do you think?
Most professors do it the first way.
So separate it as far as possible from the.
Yeah.
That's not a good reason not to do it. If most professors do it, then I think we should do it. If most professors don't do it, we should do it.
Gary Eden's philosophy was that, you only have so many chances in your life to go outside of your field. So.
But let's be honest, how many of you are going to switch careers after a presentation in this class? Probably that's a low probability. Who said? Oscar Wilde said that if you find yourself siding with the masses, it's time to sit down and think about it. I don't know, probably we should keep it separated for now. What do you think? What I'm going to do is for the exam Tuesday, you're going to find a number on your exam. You're going to pick it randomly from a stack, and that number will correspond to your project. So that will be a done deal. Okay, let's do it the usual way. Okay, coming back. So we have this breathing mode of the cube, of the particles, and the way you write so this is problem C, the way you write the coordinate of each particle is basically 1 b/2 plus 0,1 cosine of omega t, and then this is the usual x, y, z, right? So this is kind of nice factoring out. Okay, so when you write the S of Q, it will be the sum over J of e to the I Q times this thing. So 1 plus 0.1 cosine of omega t, we have B2 somewhere, and x, y, z. No, that's it. No x, y, z. This is qx, qy, qz, right? So what do you think this is going to give you? So imagine I have the pairs, right? So I have, let's say, instead of 1 to 8, I say 1 to 4 of this plus its complex conjugate. So this all together is going to give you a cosine of qb/2 1 plus 0,1 cosine of omega t. Okay, so basically these are plus minus b/2 plus minus b/2 plus minus b/2, right? Yeah, so this is not entirely accurate, but so plus by b/2, then you need to switch them around. So you are going to get 4 cosines, okay? So you get cosine of something plus cosine under the. So your time dependence will be in the argument of the cosine. Are you with me? What's that going to give you? Huh? Well, if it's what?
It's not Doppler shift, it's something.
It is a Doppler shift, essentially, right? I mean, you're scattering stuff from a moving. But the interesting thing is, so you can expand this cosine, right? So you get cosine of a cosine of something. You can expand it as in Bessel functions. So it's going to give you something like A omega plus B omega squared. That's how you get harmonics. So that's what I wanted you to kind of see, that my thing is breathing in and out at omega, frequency omega, but my field, scattered field, actually is going to have harmonics. So you get the fundamental omega, but you also get omega squared, omega third, and so on. And it always comes from the fact that because of the cosine of a cosine, because your phase goes as a cosine. If your cosine was in the amplitude here, then you would get just a simple harmonic omega frequency. But because your phase has cosine in it, you see, you will get also the harmonics. Do you see the difference? Or no? It's the difference between cosine of omega t, which is a nice sinusoidal function, versus cosine of cosine of omega t. Very different. The second one has multiple harmonics in it. Yeah? Okay.
So it's no longer an LTI system?
Why do you say it's not L?
It's not linear.
Because you're generating multiple frequencies? The system is still linear, but this is actually a tricky question, to be honest with you. Because whenever you have a Doppler, this is a Doppler shift, essentially, right? Your chi does not depend, your response function does not depend on your incident field. Okay, so the response is still linear. But with the Doppler shift, you manage to generate new frequencies. Okay, so
It's not time invariant because it depends on when you start shining the field and what state the cube is breathing at, right? If the cube is small and then expands at time equals 0, or if it expands and going down at time equals 0, that difference is not time invariant, right? It has some state prior.
Yeah, you can think of it that way. Because essentially your response function is time varying. Yeah. Okay, so maybe that's one way to put it. But this calculation will explain Raman scattering, which is actually, because you're generating new frequencies, it is actually a nonlinear effect. That's why the conversion is so actually very small. From a fundamental to Raman shifted light. You get only 1 in, I don't know, a billion conversion. But for example, reflecting light off of a moving mirror, I wouldn't call that a nonlinear interaction. But maybe, yeah. But you get new frequencies. You get the Doppler shifted frequency.
Of a still mirror?
No, of a moving mirror.
Of a moving mirror?
Yeah. Something to think about. Okay. So you do get an intensity that will oscillate at omega, but you also get higher harmonics, which I thought was an interesting observation. Now, since we only have 2 minutes or 1, rotating the thing. I mean, this is like before, really. So if you rotate your cube, is not no difference than before. You just write your theta as omega, should be a different omega probably, right? Omega prime t. And you do that rotation coordinate like we did before, compute everything. And now I think that's where people really gave up, was like combining the two. So basically, what's the relevance of this? So you have a molecule that both rotates and vibrates.
Molecule, basically, a real molecule.
Any real molecule will have both, right? Yeah. So for the dipole interaction, the vibration will be somewhere infrared. You go to rotational, you end up in the microwave, so lower energy for rotations. But they always coexist. And I mean, to solve this problem, you just need to look at the coordinate of each. So there will be a vibration, and then that whole thing will be rotated with your rotation matrix. So it's a matter of just taking the vibrational, that d of t equals b over 2, 1 plus blah, 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 and now projected that to the rotation matrix, and you're done. But the deeper question is, what happens when my molecules do this and rotate at the same time? How is that changing my spectrum? And usually what we do is, it's an approximation that says that during vibration, there is no rotation. So you know what I mean? So the vibration is much faster than the rotation. So that's how we usually compute the modes for each molecule. I think this is called the Born-Oppenheimer approximation.
Is Oppenheimer like
The DSP guy from
DSP guy?
I think it's,
No, it's the quantum mechanics guy.
yeah.
There's a digital signal processing guy, Oppenheimer? Oppenheim? No.
Is the Manhattan?
Yes, that guy. Well, I mean, you see what it really means is that we like to decouple things. So I take care of the vibration mode independent of the rotation mode. Okay, so this is a useful approximation that says that the nuclei do not rotate during this vibration. So it's kind of doing this very fast and slowly rotating, right? Okay, anyway, I hope you enjoyed the whole process. I mean, without any preparation, this would have looked like a crazy complicated problem, but I thank you. But I think now you're able to do complicated problems. That's the whole point. So think of the DNA, think of these, all kinds of other shapes. Yeah, find the Fourier transform of a spiral. It's in Dick Blayhut's book, the former chairman of our department. That's where I found it. So I made a homework problem out of it.